Hello, YouTubes, and welcome to the Ace Math Normal Curve Review. Yeah! Yeah! I thought this would be worth some review time because the process for using normal curve, it's not the most complicated, but it really helps to understand the reasons why. And if you understand those reasons why, these problems are really easy. So let's talk about it. First, something that you can easily overlook is what is normal data. We know data is just a group of numbers. And if you were to graph those group of numbers in like a histogram, the connected bar graph, and then you looked at your picture, if the picture looks like this guy right here, we call that normal. So what does it look like if it's not normal? Well, over here we got 3 examples that violate some of the rules of being normal. What are the rules? We got 3 of them. Number 1, unimodal, like mean, median, and mode, the most, which just means there's one big bump. 2, symmetric. I think we know what that means. And finally, when you calculate the standard deviation of the data, which means if you had all your data points and you did that really annoying long process where you do like add everything up and take the difference and square it and then do the average and then take the square root, and then you discovered that around 6 deviations kind of gave the range for nearly all of your data, 99.7% of it. That's what we're looking for to be normal. So over here, this one's no good. We call this skewed to the left. It ain't symmetric. These guys are no good because they ain't unimodal. And finally, you might have data that appears normal, but if there's too many standard deviations, like in this case 1, 2, 3, 4, 5, 6, 7, 8, it's too many. It doesn't count. Now, why are we talking about all this? Because if data is normal, the idea is that we got some tricks we can do. We can make some predictions, since this is a very predictable situation. It doesn't mean it's necessarily good or bad, because like we've talked about, there's plenty of these non-normal situations that come out in the real world all the time. For example, this could be a test where most people did pretty well on it. This could be a test where a lot of people studied and did well, and a lot of people didn't study and did poorly. So it's still symmetric, but it's not the same as the symmetry over here. And finally, this could be a test where just the data is more spread out than normal, even though it's still symmetric and unimodal. Okay, so what can we do if it is normal? Well, we got these formulas down here. We can use z-score. And what does z-score do? It can tell you the exact percentile of a data point. The best example to think about this probably is a test. The IQ test is a famous one, or the ACT is another good one. Finding your percentile is like finding what percentage of people you did better than. And this process is a way to figure that out. Okay, so let's take a look. Z equals x, that's your data value, minus Greek letter mu, that means the mean, minus standard deviation. We do this to locate where the data point is on the curve. We call it the z-score. Here's the critical thing. That name, it's kind of weird. It's kind of unneeded. We should just call it the amount of standard deviations. That's what a z-score is. And we go to the left by just making that number negative. Finally, down here, we have this notation, this Greek letter, I think it's phi. But this is just our way of connecting a certain z-score which just means how many standard deviations to the left or the right something is, with its percent. Now we figure out the percent by looking in one of those tables with the normal curve on it. But this is just our, notation of writing that. Okay, so let's look at some problems. Oh, real quick, one extra thing. If the problem ever starts off within parentheses and some stuff, that's another way they can tell you the mean and standard deviation. The second number is the standard deviation squared. So if they said, all right, here's the situation, n 3.5 comma 4, it just means that 3.5, that's the mean, and 4, we'd have to take the square root of this to get the standard deviation. And if you recall, the standard deviation squared, we call that the variance. Okay, let's look at some examples. All right, here we go. We're imagining we got a data set. They tell us the mean is 5. The standard deviation is 1.11. The first thing you do on all of these problems, every single time, draw the picture. Do it as fast as you can if you want, but it really helps frame the answer, and it makes sure that you won't make a mistake. A lot of times I realize I've done a mistake in my process just because my answer doesn't seem reasonable, it doesn't seem right looking at my picture. So over here, if they gave us this notation, they want the percent to the left of 6.53. So I know if to the right of 5 we have 3 deviations that are all around 1, I'm going to estimate 6.5, I don't know. It's probably right here, and thus, since we want the percent to the left, we want all this percent. Just by looking at it, I can guess, something over 50%. So let's go to the work. We put it into our formula. We find the distance from the mean, divide by our number for standard deviation, and that tells you how many standard deviations to the right this data point is. Recall the difference. This is how many units one standard deviation is, but this is the amount of standard deviations from the mean. It's like saying there's 12 inches in a foot, but then I've walked 4.3 feet from where we started. Now we have to find the percent that goes to this. And to do that, we need the chart. Now it might be kind of hard to see here, so I apologize. But at least we can talk about the process of using this thing. Here's one of them from the book. So our z-value here is 1.378, which means 1.378 standard deviations. How would we use it? First, we would find 1.3. It's right there. Boop. You can use a piece of paper on the ACE test to kind of help you keep things straight. Then we need to go 1.37, so we go over to right here. We have one more decimal place, and that's 8. Looking over from the 8 is right here, and I see this number 13. We need to add that number to the last 2 digits of 0.9147. So I have the work here. 0.9147, that was the percent that went with up to the 100th decimal place. And 13, that was kind of the extra percent we add because of the 1000th place of 8. Add them together, you get 91%, which is a lot, but I was expecting something over 50%. Okay, what if they want the percentage below something? 3.72. How is that different? Well, now we are to the left side of our curve. So just by looking at our picture, something small is what we're expecting as the answer, certainly well less than 50%. Okay, same process. We jam it into the z-score formula. We find our distance from the mean And notice this time we get a negative answer. We expected that because we're on the left side of the normal curve. Now here's the thing. If you look in the table, you will find no negative z-score values. They start at really 0.0 and they go to 2.9. No negatives. So instead what we're going to do is find the positive for 1.153. And our plan is we'll minus that from 1. That's the process of what you do. We can make sense about that thinking back to the normal curve, and it's all about symmetry. For example, if we find the z-value, let me try to make it look symmetric here. If we find the z-value that goes with positive 1.153, then we found all of this percent over here. All this and all of this. Well, clearly that's not what we wanted. We wanted the percent of this space. Also the same thing as the percent of that space. So by finding the positive percent, we find all this. We minus it from 1 to find this little piece, and that's our answer because that's the same piece as the piece we were after. So look this one up in the table. The positive gave us 0.8755. Minus it from 1, and we have this 12% answer, rounded to 3 significant decimal places. Okay, what if now they ask for a percent greater than to the right? Not much to do differently. We just start off with that data point, do our z-score process, find the z-score, the amount of deviations. We look it up in the table, and I get this, 96%. Now this little piece here does not look like 96% because the z-score table always gives us the percent to the left, same as percentile. So that's why in the last problem, in the same way, we minus from 1 and we get around 3%, which looks more reasonable based on our picture. Okay, finally, this is kind of like a double whammy. They want the percent bigger than 3. Why is this a double whammy? Because it's to the left side, but they want the percent above the value. And you'll see why this is a double whammy, or like a double negative in the work. So we find the z-score. It's negative 1.802. We know that's negative, so our process is we need to do 1 minus the positive, as seen here. But since we want the percent to the right, as soon as we get that answer, we have to minus it from 1 as well. So rather than minus from 1 and minus from 1 again, if you look at the work, that would just undo itself. And it's the same thing as just finding the percent that goes with positive 1.028. And we already looked this up in the last problem, and it's around 96%. The flip of these normal curve problems, if rather than giving you the mean deviation and asking about a specific data point, they could flip them by giving you the percentage or the percentile and asking you what was the data point that went with it. Okay, so here's an example here where imagine we're still talking about a mean of 5 and a deviation of 1.11. So we need something that has more than 30%. Boop, 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 boop. So we're looking for this x value. Now let's talk about this because I think this can easily confuse people. At least it did on the last quiz. More than 30%. If this was a problem that we were just looking at, one where they gave you the x value and they use the word more than, they'd probably be asking what percent is more than a certain x value. And we know that more means the same thing as above, which means the same thing as to the right. Here, this is a different situation because they're starting us off with the percentage. So when they said, what x value goes with a data point that has more than 30% of the total 100%, that's just how it normally works. Remember, the z-score table gives you percent to the left, so if this is your data point, you could think of it as doing better than 30% of everyone else. This is like the 30th percentile. So hopefully that explains all that stuff. So we're trying to find now the z-score that goes with 0.3. Obviously, can't do that because there's no 0.3 in the table. Instead, we're going to flip it, and we're going to find the z-value that goes with 0.7. We look up 0.7 in the table. It's not there, but you can find as close as possible, like a 0.69, something very close, and adding the 100th place gets us as close as we can. I'm not going to really go over this process, but the z-score that goes with it is 0.524. So this is using the table backwards. Don't forget, this is not the z-score we were after. This is the z-score that goes with the 70th percentile. We want the 30th percentile, so we have to flip back over to the left side by making this number negative. So there's the process. You find it, you make it negative. But thinking about the picture will help make that easier to understand. Rather than find the 30% over here, we find the number that went with the greater 70% over here. We find this positive number and just flip it to its negative counterpart. And you can see how it works because this little piece here is symmetric to that little piece there. Once you get this negative z-score, we just plug it into the formula. Look, the only unknown here is x. So you just multiply both sides by 1.1, add the 5, boom. There is your data point. Did I do this right? 5.59. Okay. I'm not doing a redo of this video. It's taken too long. But I think this is one of those examples I was saying where just by looking at the picture, I know my answer is wrong. So if this was the actual ACE test, I get a wrong answer, I can realize it's wrong, boom, I instantly can go back and fix it. To save us time, I'll talk about the fix in the comments for the video. But, I don't know, in real time, at least you can work on evaluating your answers. Finally, here's one where they gave us a percentile that goes with 7 and a percentile that goes with 13. I didn't really formulate the full question, but the thing they would ask you for is what is the mean and what is the standard deviation. Here's how it would work. You basically just do the process we did with the 7 and do the process with the 13. So here we're imagining, since 20% is to the left, we go with 80%, we make it negative. 55% is to the right, so we just look up and we find two different z-scores, negative 0.842 and 12.55. You can plug those back into the z-score formula and you get two different equations. Notice in the problem above, if you can still see it, we just got one equation. But this was cool because look, there's only one variable here to solve, x. Down here, the difference is they told us the x value in the given info, 7 and 13. What they didn't tell us was the standard deviation, or the mean. But that's okay. Hopefully you've figured it out by now. Looking at both of them, we have a system of equations. Two equations, two variables, so all we have to do is substitute and solve. There are different ways to do it. I went ahead and got standard deviation by itself in both of them, set them equal to each other, cross-multiplied, distributed to both the terms on the top, and then just solve for our one variable of the mean. It got it by itself, plugged it back in to find the standard deviation. And these answers looked reasonable based on our picture. Okay, there's the normal curve. Hopefully this review helped. Peace out.